To everybody to this Severo Ochoa colloquium of EFIC. So today it's a pleasure to have with us Gia Vali. He is originally from Georgia and he did his PhD at the University of Tiflis, but he has been working in a lot of places like the ICTP Trieste, ISA and CERN, and now he's professor at both the University of New York and the Ludwig-Maximilian University in München and the Max Planck. And I know that all of you know him because he is one of the authors of the models for extra dimensions, trying to solve the problem of the hierarchy problem. And he's also working in the interplay in the interdisciplinary field of particle physics and cosmology. And today he's going to talk us about black holes and the secret life of black holes.
Okay, thank you very much. It's a great pleasure to be here. And so I will describe, I don't know whether this microphone works, but I will describe some ideas that, some relatively recent ideas about black holes and what is their life quantum mechanically. So these are, okay, the number of papers. These are incomplete list of my collaborators, actually, two of my students, Sebastian Zell and Arnold Sebastian Sia, Marco Michels. So these are mostly with Cesar Gomez. These ideas were developed with him. Now, I will use units in which speed of light is 1, but I will use h bar, Planck's constant, explicit, at least for the time being. So G Newton is Newton's constant, and as you know very well, you can make up a quantity as something that has dimensionality of length by multiplying Newton's constant by h bar. And this length is an extremely important length scale of nature, probably the most important length scale of nature, most fundamental at least. This is the Planck length. And there is an associated mass scale with this length scale, which is the Planck mass. Now, Planck length is very small, it's approximately 10 to the minus 33 centimeters. And the Planck mass is correspondingly huge for particle physics scale. It's a mass of amoeba, actually, one cell organism. So in that respect, you can say that we are made up by cells of Planck mass cells. So now let me move to black holes. Of course, this length scale plays a crucial role for quantum gravity, the Planck length. And both Planck mass, and so will be central in our discussion. So now, what are the black holes, right? So classically, if you have an object of a mass, certain mass m, this object has an associated radius, which we call a gravitational radius, which is, or Schwarzschild radius, which is twice Newton's constant times that mass. Now, what is the physical meaning of that radius? The physical meaning is that if we contract a given mass to that radius, it becomes a black hole. So escape velocity becomes speed of light and so on. Okay. So every object that exists there, any form of energy, if you can go into the center of mass of that energy, has an associated gravitational radius. And correspondingly, there is always a black hole to which you can collapse this particular object if you make enough effort. Now, for example, if you take gravitational radius of the Earth is approximately a centimeter, gravitational radius of the Sun is kilometers, like 3 kilometers or something like that, and so on. Okay, so every form of energy, every form of mass has the associated gravitational radius, and so it has a black hole counterpart. Okay. Now there are many things about black holes that are sort of mysterious. You probably heard many times, but the ones that I will focus in this talk is mostly connected with their quantum properties and with the way they process information. Okay. Now, okay, so what are the properties of black holes? First of all, immediately in classical physics, black holes have interesting properties in the sense that they are featureless. Okay? In other words, normal objects that we have around us, they have features, right? So they have colors and shapes, different colors and shapes, and high multiple moments and different distributions of density and so on, right? But for black holes, there are very, very good arguments, very precise arguments, which go under the name of so-called no-hair theorems. That in classically black holes, they carry essentially very few features. Okay, so for example, the features that black holes carry are mass, given by mass, angular momentum, charge. Okay, and I don't want to go into some small exceptions, but generally, in general, this is the story. Okay, so if we, for simplicity, if we put black holes to be non-rotating and have zero electric charge, then the only characteristics is the mass for this black hole. Okay, which means that so it's very strange, right? But after all, okay, that's how it is in classical physics. But what does this mean from the point of view of information? Okay, this means that since black holes have no content that you can distinguish, so other than, let's say, if I want to send you a message, right? Normally, when I send you a message, I encode features. I encode message in features. Okay, I have to write letters, rearrange these features, okay, and so on. And that's how I can send you a message. Okay. Now, if I send you a black hole because it has no features, classically, naively, it looks like, naively, again, I would say, it looks like that I cannot send you any message using a black hole. Why? Because black hole has no memory. If I write a book or a letter and then collapse it into a black hole has no memory about the initial state that gave you this black hole. Okay? So if I send you a message with this black hole, for you it's just a black hole. And so naively it looks like that I cannot send you any information using a black hole. Okay? So from here, naively, you would conclude that a classical black hole carries zero information. Okay, nothing, almost zero. Okay, nothing. However, when you go to a quantum theory, and if you want to think about a classical black hole coming from quantum theory, you will discover a puzzle. Okay, let me now describe this puzzle. Now, usually this puzzle is not presented in this way. If you go to, I mean, in general presentations, I've never seen it presented from this angle. Okay. Now, first of all, okay, some remarks about quantum theory, right? So, the quantum theory, when we go to quantum theory, okay, quantum theory brings us new things. Okay, we live in a quantum world, of course, that we cannot change. So this comes with Planck's constant. Now Planck's constant is very small in normal units that we use, on macroscopic units that we use in everyday life. And so that's why it looks like naively that we live in a classical world from our everyday experience. But this is an illusion. So now why do we have this illusion that we live in a classical world? In other words, what is the measure of classicality? Okay, where can you say that something is in a good approximation classical or it's quantum? So the measure is the action, because the h bar, Planck's constant, you can think of it as a quantum of action. Okay, I mean, not in the sense that necessarily action should be quantized in a process, but it's a sort of, it's a characteristics of an action, okay? And now so if you have a process for which action is much bigger than h bar, then this process typically is in a good approximation is classical, okay? So for example, if I move around in this room, this action or this process when I move around in this room is huge compared to h bar, and that's why my motion can be described classically pretty accurately, okay? So this is a measure of classicality. Now, another thing that quantum mechanics brings to us is the uncertainty principle, right? So we have fundamental uncertainty in nature. Okay, so there is no free lunch. This is what Heisenberg is telling us. So what does this mean? This means that if you want to measure or have a very precise account of the energy in your process, you have to invest a very long time, okay? And correspondingly for momentum and the distance. Now, what does this imply for us, for this colloquium is that, Heisenberg is telling us, quantum mechanics is telling us, that information costs energy, okay? Why? Because in quantum world, the building blocks in quantum world are particles, elementary particles, okay? And elementary particles are the most elementary thing you can do with the vacuum, okay? If you have a vacuum, nothing, and you want to do something with this vacuum, the most elementary thing you can do, you can populate it with a one particle state, okay? So correspondingly, if you want to encode information in quantum theory, you always encode information in states, okay? So you create state, which is different from your vacuum, and somehow you encode information in this state, right? Now, to create state, you have to create particles, okay? But now, if you want to create particles, particles are costly, they cost energy, okay? Which means that information necessarily costs energy. Now, in particular, for example, if I want to send you a very compact message, 1 bit of message, suppose I want to send you 1 bit a letter in which there will be 1 bit of message, yes or no, okay? Now, this bit we can encode in a particle number, for instance, a photon. So I can send you a small box, you open it, and there is either 1 photon or 0 photons in this box, okay? And that will be the bit of information. But you can see immediately that there is a limit of how compact this information could be, okay? Why? Because if I want to send you a very compact message, I have to encode it into a short wavelength photon, and this costs a lot of energy, okay? So this is fundamentally different from classical physics, okay? Because in classical physics, you can send an arbitrarily large message, an arbitrary amount of information, you can encode in an arbitrary cheap energy state, okay? Now, by the way, this is a little bit interesting because you hear many times that quantum computers are much more powerful than the classical computers, right? This is true, but they are powerful in a different way. In a sense, if you compare two observers, two civilizations, one lives in a classical world and the other one lives in a quantum world, the civilization that lives in the classical world is much more superior as far as information storage is concerned, because classical observer can store infinite amount of information at no cost. The quantum observer cannot. So because we are quantum observers, we have to pay the price. And this is absolutely fundamental. And it's also fundamental for black hole physics. Now, the point is, however, the interesting things start when you put on top of what quantum mechanics is telling us, gravity, okay? Even Newtonian gravity or general relativity, doesn't matter, okay? And you don't have to quantize gravity or do any exotica like that. Simply, we know that even classically classically energy gravitates, okay? Which means that information gravitates, period, okay? So if you want to store a lot of information somewhere, that something, your storage, becomes more and more gravitationally important, okay? So, in other words, if I, let's say, store more information in this computer, by storing more bits, I make this computer a little bit more heavier. Of course, in everyday life, we don't notice this because this computer is very far from being a black hole. But for black holes, this is very important, okay? In other words, if you have a box with information, this box, if you put the information, starts to gravitate, inevitably. And more information you put in the box, more it gravitates, okay? So, this means that, now suppose I give you an imaginary box, okay? And I ask you to do something with this box, okay? To do as much information as you can in this imaginary box. Sooner or later you have to run into a problem, okay? So the question is, what is this problem? Because sooner or later your box will gravitate so strongly that it will become a black hole. And once it will become a black hole, then if you start putting more information, this black hole will grow. So in other words, it's telling you that there is a limit to how much information you can put in a given size in a given region, okay? And this is extremely important. Now the consequences from here, there are two consequences, okay, at least there are many, but okay, there are two very important consequences. Because immediately you realize that because information gravitates, nature has a shortest wavelength, a shortest length scale, okay? So in other words, there is a limit to how small can be a scale, a length scale, that you can resolve. And this limit has nothing to do with how sophisticated you are in inventing theories, okay? Because as long as your theory obeys the rules of quantum mechanics and obeys rules of classical gravity at large distances, which of course every normal theory obeys, then this statement about the shortest length scale of the nature is a necessity, okay? So this is the shortest length scale of nature is the Planck length, which is 10 to minus 33 centimeters, as I described. And that's one of the importance of this length scale. That this is the shortest that we can see, okay? Now, why? Again, we can understand it in a simple terms, right? Because let's say this is a Planck length, let's say, right? And imagine that you want to resolve. I give you a Planck length, and you have an extremely powerful microscope. Let's say our civilization, if we wait sufficiently long, will become infinitely powerful, let's say, and we want to resolve length scales shorter than the Planck length, okay? So you have a box of the Planck size, and you want to look inside the box and see substructure in this box, okay? Now, you have to do experiment by scattering extremely short wavelength particles, okay, in this box. For example, you can send there an extremely short wavelength photon. The photon with wavelength much shorter than the size of the box. And do scattering experiments with it, okay? Now, however, the problem is that the photon has an energy, okay? So so inevitably you have to localize energy on a distance shorter than the Planck length if you want to do measurement. But if you localize energy, but then there's a corresponding energy cost because you have to localize the wavelength because we are in quantum mechanics. And so what will happen? You can estimate it very easily that once you start localizing photon at the distances shorter than the Planck length, the photon, the gravitational radius of the photon will become bigger than the Planck length, which means that photon will become essentially a classical black hole, okay? So in other words, this is the way you bounce back from the Planck length. You cannot resolve distances, sub-Planckian distances, okay? Now this is, you see, the arguments that led you to this conclusion are very simple, right? We just put together quantum mechanics and classical gravity without going into any sophisticated thing. But the consequences are absolutely profound. And sometimes these consequences are not appreciated, and then that's how people end up writing non-existent theories, okay? Now, what is another consequence of this fact is that you have an absolute bound on information storage. This is a so-called Bekenstein bound, and what is it is what I said. So if I give you a box, and I ask you to store information in this box, you can put there a lot of particles, okay? So you can try to store information maximally softly. You see, you can try to, if I give you a 1 meter box, you try to do your best not to disturb this box by putting there 1 meter wavelength photons or 1 meter wavelength particles, okay? As soft as possible. But doesn't matter how soft they are, since they have finite softness, because box has finite size, inevitably, sooner or later, the box will collapse into a black hole. And after that, it will simply grow. Okay? And that is the bound that gives you bound on how much information can be carried by a given region of your space, and that's Bekenstein bound. Now, it's interesting that this information, okay, this measure of information, entropy, scales as area of the region. Okay? Not the volume, but the area. Now, the fact that it scales like area, and notice that it scales like area in Planck units, which makes sense because Planck, as we said, Planck unit is the smallest pixel that you can have in nature. So it's an area in Planck units. This, of course, I'm discussing three-dimensional space-time where we live, sort of. We can generalize this to high-dimensional. It's always an area. Okay. Now the fact that, so this creates an illusion, right? Or reality, we don't know, right? But the illusion is the following, that if you have a black hole, it saturates Bekenstein bound on information storage. And then so it looks like, okay, this is the impression, right? The impression you get is the following, that as if the surface of a black hole is divided in Planck-sized pixels, as if it's like a screen, and as if in each pixel there is a degree of freedom that could be in two states. So it's like you have a little creature living in each pixel, and we can have you can have a flag up or down, okay? And that's the way information is accounted for. And now this led to some people that started with Toft to call this a holographic principle. In other words, that the scaling makes you think that as if the entire information of a black hole is stored on a surface. However, we don't know whether this is just a way of bookkeeping or these degrees of freedom that live on the surface are real. Okay? This is a separate story. But the way you can do accounting as if there is something living on the surface, at least the information is carried on the surface in the Planck-sized pixels. Okay? So this is what quantum mechanics brings us, and now we want to go from classical theory from quantum theory to classical theory. Okay? Now, what is classical limit? In other words, in any quantum theory, you can take classical limit, and when we take classical limit, we should discover classical physics. Okay? So now the classical limit, as we teach students, is when you take h bar to 0, Planck's constant going to 0. Okay? Now, when you take h bar to 0, because h bar, and keep everything else fixed. If you want to take classical limit, that's what you have to do. You keep Newton's constant fixed, and you take h bar to 0. And what happens? What happens is that Planck length goes to 0. Okay? Now, if Planck length goes to 0, this means that information stored by a black hole, as computed by a quantum physicist, goes to infinity. Now, this contradicts to what naively I told you 2 or 3 transparencies ago, because I told you that classical black hole is featureless. If it's featureless, you would tell me how can this object carry an infinite amount of information? How can a featureless letter contain infinite number of information? Okay? And so, okay, this is the small puzzle that we encounter. Now, the thing is that, okay, so to resolve this puzzle, you have to reconcile 0 with infinity, okay? Right? Now, as you know very well, it's very hard to reconcile finite numbers, which are different. For example, I cannot reconcile 1 with 10, but 0 with infinity you can. That's the thing, right? And okay, we'll see how that happens.
You can reconcile, you change the units.
No, in the same units. No. Here I'm not changing units, because if I would change units, of course, my talk would not be informative. So, of course, it's very important that we fix units from once and forever, and then we work in the fixed units. We only change parameters of the figure. Right. No, thanks for the remark. So let's try to understand this from the quantum information point of view, right? Now, information, and especially quantum information, it has its own rules. These are rules of quantum mechanics, when you want to think of quantum mechanics in an information sense, and black holes cannot change it, and also gravity cannot change it, because these are universal rules coming from quantum physics. And in my talk, I'm not going to change quantum physics, okay, for sure, okay. Now, then you can ask this question. I mean, if I have a black hole from the point of view of information person, a computer specialist, or what is a black hole? And well, okay, as any other information, any other message, you can write in a binary code, and so it's a sequence of zeros and ones. Okay, so the black hole is just a sequence of zeros and ones. Now, who is responsible for these zeros and ones? So there is a sequence of numbers which can be in two states, 0 or 1, let's say, right? And so these are certain degrees of freedom. You don't have to know who they are. So say, some people can tell you that these are holographic degrees of freedom or something else. You don't have to know who they are, but you know that there are some degrees of freedom because of this entropy, okay? So there are some underlying degrees of freedom which somehow appear only when your system collapses into a black hole. They are not there before. They appear when system collapses into a black hole. And then using these degrees of freedom, you can write a message, and black hole is this type of message, n long, okay? Now, you can see why this is the case, because these degrees of freedom in quantum mechanics, they are called, in quantum information, we call them qubits. So this degree of freedom can be in two states, two basic quantum states. It also can be in the superposition. I'm not discussing this for a moment. So it can be in two states, 0 and 1, okay? It could be a spin, for instance, up or down, or some isospin up or down, whatever you want, okay? Now, of course, if you have n distinct degrees of freedom, then you have 2 to the n possibilities. And so this means that you have 2 to the n microstates of this object that classically looks identical to itself, okay? So this means that when I get from you a classical black hole, somehow this black hole can be into 2 to the n different quantum states, which I cannot distinguish classically. So when you tell me, if I'm a classical observer, for me this black hole looks the same, okay? And so that's how the message is written. Now the thing is, the question is, what are the proper characteristics of qubits? And of course, one of the important characteristics of qubits is the energy gap. In other words, what is the effort you have to take to bring from down to up, or vice versa, okay? Now, and here is the whole point, because the point is not that black hole gives you many qubits. That's not a big deal. I mean, you can arrange these qubits in laboratory, no problem. You can have spins, for instance, a system with spins located in different places. You can have arbitrary number of those qubits. That's not an issue. The issue is that the black hole, in order to have the properties that we discussed, must have these qubits which are extraordinarily cheap in energy, as almost gapless. Okay, and this is the point. Okay. Now the energy gap, in order to tell you what is the real mystery about black holes, is this. Okay. And unfortunately, it's not discussed usually in this way, all right? At least it's not very common. I've never seen it. Now, let's make it very dramatic, okay, to understand where the puzzle is. Suppose I give you a normal system, quantum mechanical system. I don't know, I give you this computer, for instance, okay? And, okay, it has certain size, okay? This computer has certain size. And just based by your intuition with the uncertainty principle, you expect that the minimal levels of this object, energy levels, okay, they are given by inverse size of the object, okay? Typically, that's what you have, right? Okay, could be some parameters, parametrically this may be different, etc., but typically this is the story, okay? So in other words, if I give you a box and I ask you to put the 1 bit in this box, let's say excite the first level in this box, this is the energy price you pay, okay, typically. Now, however, if I have a black hole of the same size, so now I'm comparing a normal quantum mechanical system of given size and a black hole of the same size. And what black hole accounting that we did is telling me that actually to put 1 bit here costs energy, which is h bar divided by r, but to put 1 bit here costs h bar divided by r divided by 1 over n, where n is this black hole entropy. Now, n is enormous. To give you some sense of numbers, let's compare the following thing, right? For instance, if I give you a box of 1 centimeter size, so box of 1 centimeter size would be approximately a black hole of mass of the Earth, comparable to the mass of the Earth. And now I give you a normal quantum mechanical system of 1 centimeter size, a box, let's say, or a potential well, 1 centimeter radius, and a black hole of Earth's radius, okay? Earth's mass. And I ask you to store the 1 bit of information, okay, related to 1 bit. Now, the energy you have to invest in 1 centimeter object is approximately 10 to the minus 4 electron volts. Let's measure it in electron volts. And energy that you have to invest in a black hole is 10 to the minus 70 electron volts. Now, you can imagine how cheaper the black holes are for arranging this 1 bit of information. And this is the mystery about black holes. How the system manages to produce qubits which are so extraordinarily cheap, so that they essentially they go counter to your normal quantum mechanical intuition, because normally you think that the energy should cost like inverse size, okay? So what interests me personally in black hole physics is how these qubits appear, and what are the physical systems, how physical systems manage to give you such an extraordinary chip, energy qubits. Now, so what are the approaches? Okay, so now one approach which sometimes works, and actually sometimes works pretty well, is that when you have a system which is mysterious, and this system has certain property, okay, but the system is very hard to compute, okay, then usually to understand this, to resolve the mystery, what you try to do, you try to look for the same property in the systems which are computable and which are simpler to compute. And then you try to understand, are such properties really unique to these systems that are extremely hard to compute, or they also appear in other systems that are much easier to compute, okay? If that's the case, then you can make a hypothesis that this phenomena, this property, mysterious property, is because of certain universal phenomena which can take place in many different systems. And so, okay, so this is the approach, one approach you take, and then you see if it works or it doesn't work. So this is our approach, okay? In other words, look for the universal phenomena. Maybe what black holes do is not exceptionally black hole property. Maybe there are other systems, both in quantum field theory or in condensed matter physics or atomic physics, which actually do the same, but it's just simply we never looked at them, okay, from this perspective. And let's see what happens. Now, we need some guidelines. So where should I look for? What is that I should look for? Okay. Now, in order to have these guidelines, we need to understand what are we dealing with. Very general properties of gravity. Now, in gravitons, in gravity, we have gravitons. Okay. Gravitons are quanta of gravitational field. And just like photons, they are normal particles, except they have a spin equal to 2. So both gravitons and photons in Einstein gravity are massless. The difference is that both are bosonic particles. The difference is that photons have spin 1 and gravitons have spin 2. Okay? Now, another thing that is special about gravitons is that they interact in the way that depends on their energy. Okay, so now as you know very well, the difference between gravitational interaction and the other interactions is that gravitational interaction is sourced by energy or momentum. Okay, so anything that has energy or momentum gravitates. Since gravitons themselves, they have energy and momentum, they themselves gravitate. So gravitons are like, I don't remember who said it in the different context, I think Okun or somebody else, that they are like shining lights. So they are light that shines itself. Okay? So they are gravitating, so gravitons gravitate. So they interact. It's an interacting theory. Okay? So now, I will not go into technical details, of course, but in the quantum field theory, there is a measure of interaction, of how important interaction is. We measure, there is a universal measure, very efficient, which is interaction coupling constant. So interaction strength. Now, this interaction coupling constant, you can define it for any interacting quantum field theory, okay? And it tells you how probable, it measures the amplitude of the scattering of two particles into gravity. For gravitons, this will tell you that if I have two gravitons in the initial state, how likely is that they will interact and scatter, okay? Now, the special thing about gravity is that this interaction strength depends on how energetic the gravitons are. If gravitons have low energy, they essentially never scatter, okay? So from that point of view, the low energy gravity is the nicest quantum field theory you can have because it's almost free. Now, you heard probably many times that we don't understand quantum. There are statements sometimes like this. We don't understand quantum gravity and this kind of things, right? Now, I want to make these things very precise because in quantum field theory, there is no such thing as quantum field theory universally. Okay? When I define quantum field theory, I always define it at a given scale. Okay? And given quantum field theory, in other words, has domains of energy, regimes in which it is manageable, and it has domains in which it is not manageable. Okay? So now, at low energies, it's like the Fermi theory, right? I mean, Fermi theory is a quantum theory, obviously, right? But Fermi theory is also not renormalizable. But we can compute things in Fermi theory. We can compute beta decay using Fermi theory. We can predict beta decay. So the fact that theory is not renormalized doesn't mean that it's simply not manageable everywhere. So in other words, any quantum field theory has the domains of applicability, manageability. Okay, the domains where we can compute things. And for gravity, this is a low energy domain. In other words, lower the energies of gravitons, better computable they are. Processes are better computable. Now, the problem is for gravitons, which have very high energy or high momenta, or momentum transfer in the processes, because the coupling constant of interaction strength of graviton is their wavelength, or to be more precise, de Broglie wavelength, of momentum transfer in a process in Planck units. So now you see that if the wavelength becomes Planckian, then of course these gravitons become strongly coupled, and then we cannot compute what is going on. Okay, this is the problem for quantum gravity. Now, however, we can stay in the domain where we can compute things. So in my talk, I will not go into the domain where I cannot compute anything. Okay, this was the thing to tell you. Now, the point is the following. Okay, now suppose I ask you the following question. So let's take an imaginary box. Okay, so in order to make it simpler, let's stay in a theory with pure gravity. So suppose you are in a theory with pure gravity. Theory with pure gravity has black holes, no problem. You can form black holes out of colliding gravitational waves, there is no problem. Okay? And these are well-known things. I'm not inventing anything from that point of view. So what I'm asking you is that suppose you have a box, okay? And now try to put as many gravitons in this box as possible before it collapses into a black hole. Okay? So now you can estimate very easily that what happens is the following, that you can estimate it in the following way, right? You know how much energy each graviton brings, approximately. You know that this is h bar divided by the size of the box. You multiply it by their number, and you see when is that energy such that the gravitational radius of the box becomes bigger than the size of the box, and then you are in a black hole, okay? And if you do this estimate, you discover that universal property for any such situation is independently of the size of the box. That the black hole is formed when the number of gravitons times their interaction strength becomes crosses 1, okay? When it becomes 1. So 1 is the critical point. In other words, when the interaction strength, when the number of gravitons times the interaction strength is much less than 1, the gravitons, they cannot see each other, okay? So it's like a room of people, okay? I put very few people in the room. The room is large. They don't see each other. So they don't form any black hole or any, they do not cluster, okay? Now, if there are too many in the row, of course they see each other very well, and then all possible nonlinear processes can happen, and clustering and so on, okay? And the transition precisely happens when alpha times n is 1. So something dramatic happens at that point, and this is the point of black hole formation. This is just an observation. This is not a hypothesis, or this is not a theory, it's just an observation. Okay, so now from this observation, so this observation is telling us the following thing, that if I draw the picture of these mysterious degrees of freedom that appear when black hole forms, picture is like this. I have a system with certain alpha n, and I see that these mysterious goblets, these cheap qubits, appear when alpha n is 1. Okay? This is the observation. Now, of course, this observation is not telling me why they appear. I don't know, right? So, but this is, we observe that this is what should happen. This is what is happening because this is when black holes form. And now the point is to try to understand, are there other systems of nature for which the similar thing happens at alpha n equals 1? Okay? Are black holes exceptional, or there are other systems of nature for which the similar thing happens? I mean, this is a legitimate question. Maybe the answer will be no. But actually, the answer is yes. And what it was really shocking for us was that this phenomena, exactly the same phenomena, takes place already in the system, in the simplest system you can imagine, which is in fact exactly solvable. This is one-dimensional box with periodic boundary conditions. Okay, so ring with bosons. So you have n bosons, n bosonic particles, let's say cold atoms. You put them on the ring, and you arrange them. They should be attractive, of course, and they exhibit exactly the same phenomena. Okay, so what happens is that you have a ring, and you put huge number of atoms on this ring, and once alpha n becomes, or the 1 becomes 1 actually in certain, you have to well normalize, of course you think. This is what is happening. The Gapless qubits appear. Okay? Now, it's always good to have something which is exactly solvable, right? Because then, well, first of all, you can enjoy solving it, but secondly, it tells you that you are, it will tell you immediately whether you are on the right track or something is wrong with your idea. And actually, okay, so this is taught by my students, Wintergest and Plastic and Pritzel. And for instance, these are plots in what happens with this, how Gapless qubits appear. This is exact. This is they did exact diagonalization of the Hamiltonian. Okay, numerically you can see it. And so you have this phenomena. Now this is quite interesting because there are two things, two possibilities. Another plot here, sorry, for instance. instance, you see the sharpness of the transition. Actually, you see the following thing, that this is one particle entanglement computed. It's one of the characteristics of the transition, that you have a phase transition at the critical point. And you see, for instance, you take system with 10 atoms, or 10 particles. Oh, what happened? Okay. You already have sharp transition, but with 2000 it's like almost like a vertical line. So you see how fast system becomes black hole type with growing n. Of course, keeping alpha n 1. Sorry, here instead of Gn should be alpha n. Okay, so this tells you that. So now you can hypothesize based on this thing, because of course there are two possibilities. Either this phenomena that we observe for the system of bosons is the same phenomena that we observe for black holes, or there is a coincidence. This phenomena happens independently, and there is a completely different explanation for black holes. Okay? Now, that we don't know. We can only hypothesize. Okay? So, the hypothesis we made was that there must be something similar happening in black holes. In other words, somehow quantum mechanically, as far as information part is concerned, so information, physics of information is concerned, black holes should be understandable as some kind of multi-graviton, multi-particle states at the critical point. Okay? So, we call it self-sustained quantum criticality. Now, of course, immediately, if you make this hypothesis, you see immediately that this puzzle is, that I said at the beginning, is resolved. Why is this puzzle resolved? Because when you take h bar to 0, the n, occupation number, goes to infinity. And what happens is that qubits become gapless. Now, with gapless qubits, you have. So now, what is the story? So in classical limit, what happens with a black hole? In classical limit, black hole, when I take the quantum black hole and then take classical limit, without changing the mass of a black hole, the classical counterpart of a quantum black hole contains infinite number of gapless qubits, and these qubits are exactly gapless. Correspondingly, in order to get, now I can take this black hole, which carries infinite amount of information, and I can send you. Now, of course you will receive infinite amount of information, but to read it will take you infinite time. Because in quantum mechanics, again, there is no free lunch. Because if you have a qubit which has 0 gap, to resolve it in a quantum mechanical process, you need infinite time. So this is how infinity and 0 are getting reconciled. Because it's not, of course it's true that classical black hole, it carries infinite amount of information. But to resolve a full amount of information, full, part you can resolve, of course, on some finite time, but full amount of information, okay, or appreciable fraction of information, it takes infinite time. And that's why you see, you don't appreciate it, okay? You think of it as featureless. Now, okay, there are other things. By the way, how much time do I have? 2 minutes? 3 minutes? 10 minutes? Okay. Okay, I don't want to go into details about, okay, now, actually you can, okay, once you make this hypothesis, you can go ahead and play with these systems, of these multi-particle systems also. And actually, it's really fun, because you see that, like, for instance, those systems, they exhibit also other properties which are very similar to black holes, like they exhibit Hawking radiation, okay? Because at the critical point, what happens is that when you bring this system at the critical point, it starts to deplete. So it loses particles. And this is the counterpart of Hawking radiation that you can do in laboratory, actually. Okay? Fully quantum, obviously. And so on. Now, okay, this is very interesting because, okay, to where do we go from here? Is that, now, by the way, I must say that this phenomenon is so interesting per se that in fact, you can forget about black holes now and just investigate this phenomenon. Okay? I mean, if you want to, right? But so, for instance, they're also experimentally interesting because, for instance, this gives you a possibility to simulate a black hole type information processing in laboratory experiments with cold atoms, etc. Okay? And so you can even do some kind of quantum computing using this type of systems, okay, in laboratory. And so on. Now, let me discuss one more important application of this framework, okay? And this is about, and also evidence for this framework. Now, this is about producing black holes at the accelerators or in high energy collision. Okay. Now, this is a pretty old idea. I mean, actually not so old, 87 or something. Was initiated by Toth and then Veneziano and Gross and others, Mende and others. That okay, I mean, if in very high energy collision, you should, so if you increase center of mass energy in the collision of elementary particles, but you keep your impact parameter fixed, sooner or later you will produce black holes, okay? For example, if I take E plus, E minus, with center of mass energy of solar mass, and the impact parameter less than 3 kilometers, this collision will give me a solar mass black hole, okay? Now, the qualitative argument for this is very simple, because it's obvious that once you have center of mass energy, once you localize it within the Schwarzschild radius of its own, so any energy that you localize within its own Schwarzschild radius becomes a black hole. This energy can be stored in two particles that have very high center of mass energy, or could be stored in something else, in the star or whatever, okay? So, now, this is and there is a, okay, this was a well understood thing, and actually we even predicted with Androniadis, Nimar, Ganyhamel, and Saladin that such black holes would be produced at LHC in the context of this large extra-dimensional scenario, okay? Of course, those black holes will be quantum, they would not swallow the Earth and this kind of nonsense. But okay, so in other words, this is what I want to say is that this was well understood and at least well accepted that in high energy collision you produce black holes. Okay. However, the microscopic process behind this was not identified until at least I've never seen it. Okay. In other words, there is an enormous literature, actually very nice, very good papers written. Doing 2-to-2 collision. Okay, for example, you do collision of two particles into two, and indeed 2-to-2 collision gives you a sense that something dramatic is happening when the impact parameter becomes comparable to gravitational radius. But the problem is that to really understand what is happening, how black holes are formed, you need a microscopic theory. You cannot do it without microscope. You need some idea. The idea may be wrong or maybe right. That's a different story, but you need an idea to check it, right? And now the point is that we have this idea because we are saying, no, black holes, quantum mechanically, are multi-particle states, multi-graviton states. Once you make this idea, with the hypothesis, you can now try to see and compute black hole production in a fully fledged quantum mechanical sense, okay, in the high energy collision. And so the difference is that what we are saying is that the right process to look for the black hole production is not 2-to-2, but actually is 2-to-n, okay? Where two initial particles, they create n, large, huge number n, extremely soft gravitons, okay? So this is how the black hole state is described in our understanding, okay? Now, so I can report on the computation that we did with the collaborators here. So of course Cesar was there, Dieter Lutz, Eiserman, Stefan Stiberger. So we did computation of two gravitons into n in a domain of computation where we can compute things. And this is very important. In other words, in this kinematic regime where n is large, the final state gravitons are soft. And you are under perfect control of quantum computations. Okay? This is very important. So you can do computations there reliably. And okay, we did this computation both in quantum gravity, in quantum field theory, and quantized gravity, in Einstein gravity. and also in string theory. And so what is computation? By the way, they both agree in this kinematic regime. So string theory computation gives you precisely quantum theory computation in large N. Now, what was really surprising for us, well, probably was not surprising but was interesting, is the following. That indeed, when N is such that alpha N is critical in our definition, okay, the exponential separation factor for each microstate that you produce in two graviton collisions, so you collide two gravitons into N, exactly reproduces the black hole entropy, okay? Now, this is an extremely interesting fact per se. Again, could be coincidence. Of course, I cannot rule it out that this is a coincidence. But first, I don't believe that it's a coincidence. Actually, I'm sure it's not, okay? Because things do not have, I mean, I don't believe too much in coincidences, right? Of that magnitude, because you understand, N is like 10 to the 77. Coincidence of 10 to the 77 is a little bit too much to follow, okay? But it doesn't matter. So the point is wrong. You see, what is interesting is that somehow what we are observing. Again, this is observation. Let me not make any hypothesis. Just an observation. So you go ahead and compute 2 to N graviton scattering. Okay, honestly, reliably, in the domain of applicability of your computation. Okay, both in string theory and field theory. And what you discover is that this computation, where the naively would think this is a computation in terms of Feynman diagrams, right? So you just compute things, but of course you have to effectively solve scattering equations, etc., etc. So from that point of view, it includes some non-perturbable information. But nevertheless, this is a computation in terms of Feynman diagrams. And then you discover that this computation in terms of Feynman diagrams knows about the black hole entropy. Something that you would think is fully non-perturbative information about quantum gravity. But nevertheless, this is what we see, okay? Now, this I think is a very strong indication that, I think it's an evidence, at least an evidence, that black holes are something like multi-particle states from the point of view of quantum theory. Of course, they are not multi-free particle states, obviously. I mean, we understand that when particles are in the bound state, they are off-shell. Correspondingly, to describe them as asymptotically free gravitons is an approximation, but it's an approximation which works. Why? Because off-shellness is not terribly high. You see, that's the point. In other words, so let me elaborate on this and then I finish. Yeah, this is almost endless transparency. In other words, what do I mean? You see, when you talk about bound states in quantum physics or in quantum theory, right? So what do we mean? So let's say, when I say that this table is a bound state of molecules or atoms, or what do I mean? Because obviously molecules in this table are very different from free molecules, right? Now, what do I mean that but nevertheless we say that this table is a bound state of molecules, right? Somebody could tell me, why are you calling it a bound state of molecules? Let me simply call it a quantum state of table. And that's it. I don't care whether it's a bound state or not. Now, the reason why it's useful to think about table as a bound state of molecules is the following. That the molecules inside the table are only mildly off-shell. Okay? In other words, the momentum transfer that you need to kick them out is way less than their mass. And so, they are almost like their free counterparts. Okay? So this is the point. So, if you have a bound state of particles, if these particles are mildly off-shell, it's okay to continue this state to call it a bound state of particles, okay, of those particles. Of course, if they are way off-shell, then it's a different story, okay? Now, the black hole, they are alpha n equals 1, and they are right there. In other words, the off-shellness is order 1, but it's not like 1,000. Okay, so in other words, so that's why this approximation seems to work. Okay, this is my understanding. Anyway, so obviously now in this slide, this is again useful for things like black hole production at LHC, etc. For instance, for understanding why the signatures that we should look in, for instance, people are looking for black hole signatures in Atlas in multi-jet events. And I was keep saying this, that this is a wrong place to look for it, because before producing multi-jet events in energy, if you increase the energy gradually, inevitably you first have to produce quantum black holes. You have to be in the transition when you produce black holes which are quantum. Only then you can start producing classical black holes. Why? Because if your energy is not enough, the best thing you can do is produce black hole with n of order 1. You cannot produce black hole with n of order 100 before you produce black hole with n of order 1. But the black hole with n of order 1 will not decay into multi-jet events. It's impossible, by unitarity, by any sense, okay? So therefore, the fact that LHC doesn't see multi-jet events, that's how it should be. There's no chance for LHC to see multi-jet events before seeing two-jet events. So in other words, the first signature of a black hole will be two-jet event, most likely, and it will be very easy to confuse this black hole with another new particle or new resonance. Okay, so in other words, the bounds on black hole production should be the same as bounds on new resonances. Okay, this is extremely important. Only later, if LHC, at LHC this probably will not happen, because LHC at best has a chance to see the bottom of this resonance tower, so the first quantum black hole, and that will look like a particle. If you imagine that LHC were infinitely powerful, then the picture will be following. Let's say we have an infinitely powerful accelerator. We start increasing energy, okay? Center of mass energy. Then at some point, I should see the first resonance. This resonance will look like just another elementary particle, which will decay into two particles, or two jets. And that's it. Now, if I keep increasing energy, what I will observe after that? Now, if that object is a beginning of a black hole tower, then I should see another resonance, slightly high energy, which is slightly longer lived, and decays into more stuff. And then yet another resonance, which is even more energy, even heavier, even longer lived, decays into more stuff with lower energy. So this should be the transition from very hard decay into two jets to many multi-jet events with extremely soft jets. Okay, so this is how the transition should look like. Anyway, I don't know why I'm showing this plot. Okay, let me finish here.
Okay, thank you very much for this inspiring talk, and now we have time for questions.
Thanks. During your talk, you made a comment between the use of Feynman diagrams and the use of scattering equations. Well, I guess you described everything with the use of Feynman diagrams, but would you get any additional information with the scattering equations?
No, the scattering equations are just, it's a technicality that it's not invented by us, of course.
Yeah, I know, but...
it's a technicality which allows you to compute things more efficiently. Of course, I'm a quantum field theorist, which, okay, I like Feynman diagrams. Okay, for me, right, even highly non-perturbative process like, for example, Mercury going around the sun, the first thing I visualize is in terms of Feynman diagram. You have Sun, Mercury, and then one graviton exchange. Now, Mercury perihelium has a very nice counterpart in Feynman diagrams, which is one vertex where these two merge. I think there is no blackboard, but anyway, so you have Sun, Mercury, and then one graviton, three gravitons that are merging in one point. That's what describes Mercury perihelium. No, I'm not even, this is known. This is what describes Mercury perihelium. It's just, okay, so yes, I fully agree that Feynman diagrams, you can understand everything. Now, to compute them is a different story, of course. It's a whole thing, and that's why you need to invoke non-perturbative techniques, which, by the way, in string theory, sometimes theory computation makes it easier dramatically because of topology and this kind of things. I mean, so.
Okay, thanks.
More questions?
Well, thank you very much for the colloquium. It's been really nice. My question is, I don't know if it makes sense, but when you describe gravitons as the quanta of gravitational wave, gravitational field, is there some need for them to be fundamental, or they could be something effective that appear at some point or something like that?
Yeah, that's an excellent question. So yeah, if I so expand a little bit. Yeah, the question is, I mean, whether gravitons, we should think of them as necessarily fundamental, or they could be some sort of emergent or composite or something like this. Yeah, in this, of course, in this picture, this doesn't matter, because what I'm assuming is that even if gravitons are not fundamental and they are composite of something else, let's say they are composite or they are emergent or there are some collective excitation or some more underlying theory. Since I'm working in the domain when they look fundamental, I can use quantum field theory in which they look fundamental. So from that point of view, since we are not going, in other words, in quantum field theory language, this means that we are in the kinematic regime in which all the momentum transfer are way below the cutoff, whatever that cutoff could be, whether it's a cutoff compositeness of graviton or whatever it is. Now, on the other hand, there are excellent arguments like Weinberg-Witten theorem and this kind of, they're indicating that it will be extremely hard to come up with a theory in which graviton is really a composite object or is not, but that's a separate story. For me, it doesn't matter for this discussion. Right.
Going back to the relation between the quantum information stored inside the black hole. So you show that there is an infinite amount of information that you can store there on the surface of the black hole.
The classical one.
Yeah.
In the classical limit. Right?
Yeah. So you have, in principle, you should have zero, whereas you have infinite. But it takes infinite time to restore, to deduce this information by reading it.
Exactly.
Now, this seems something like that. There is a microscopic description of the black hole that takes infinitely many degrees of freedom.
Right.
Now, how can you extract from that those few classical information about the black hole, like the mass, the quantum, the charge, and the angular momentum, since in principle you have an infinite amount of quantum information? How can you relate that?
Exactly. So, yeah, excellent. Yeah. So again, let me make a parenthesis, a little bit parenthesis. So I want to differentiate between hypothesis and the facts that we can deduce from assuming quantum mechanics and gravity, right? Now, so the fact that, the behavior of this information as an area law, that's a fact. But this doesn't mean that you really have real physical degrees of freedom localized on the surface. This is a hypothesis, okay? So it's just the fact that it scales like area, that's what made us think that maybe there are degrees of freedom or effective degrees of freedom or some duality in which I can think of this as being a theory on a surface, okay? So it could be that these degrees of freedom are real. It could be that this is only in terms of some kind of equivalent description. In other words, I can map this to an equivalent two-dimensional theory of some sort, right? It could be that. So that's a separate question. That we can hypothesize. Now, but however, there is a completely independent the fact that you have this amount of degrees of freedom, and these degrees of freedom are what encode information. Now, your question is, since the information is like a message I saw, right? No, sorry. Here. Since this information is, when n goes to, when I take classical limit, n goes to infinity, obviously because Planck length goes to 0. And your question is, since classical black hole carries infinite information, how this information is delivered in terms of only very few numbers, like mass and angular momentum. So the answer is very simple to that question, because this means that the classical description is like an effective mean field description of your many-body system. It's like Rossby-Taevsky, basically, okay? So for condensed matter people, this is well known, right? I have a many-body system. There is a mean field description in which I can describe it classically. So the information is stored in microstates. And classically, I cannot distinguish microstates. That's why, that's the whole point, because there is one macrostate which is described by mass, angular momentum, and the charge. But this macrostate is not specifying your quantum system uniquely. There are infinite number of microstates corresponding to the same macrostate. So, and that's how it should be. I mean, that's precisely the whole point about having microstates in a quantum system. They should not be distinguishable by classical measurements. Because if they were, then of course this no-here theorem of black holes simply would be wrong. Okay? So it's an effective description in which you take mean field and yeah.
Hi, thanks again for the talk. Maybe this is just a naive question, but you said that maybe this could be like a way also to test black holes in the laboratory. And the first thing that I can think about is, how do you solve the fact that in laboratory, what I think about, for example, in this kind of system like Bose-Einstein condensate, you have some external parameters that then you tune or you change.
Right.
And then this black hole seems very autonomous, self-consistent.
Absolutely, yes.
Yeah.
Okay, yeah. Well, yeah. Thanks that you bring that in. By no means I wanted to say that you can really produce black holes in condensed matter systems. I didn't mean that. What I said is that we are specifically interested in quantum properties like information, etc. Right? Of course, these are non-gravitational systems. By definition, they cannot give you metric or this kind of stuff. But they give the counting of information surprisingly close, at least these aspects that I discussed. I don't want to exaggerate, okay? I'm saying, my question was, our question was, my collaborator, how a system of finite size can manage to produce arbitrarily cheap qubits. How this could happen, okay? Was this a property exclusively of a black hole, which has to do with some underlying quantum completion of some kind of this type of thing, like, I don't know, a very short distance quantum gravity? Or this is a universal phenomenon that you can observe in many systems. And now we have proven that you can observe it even in the simplest system. If you have bosons on a ring, you see that there is a mapping of this particular property. Of course, to go from there to full physics of black holes, I'm not saying that these objects are black holes from that point of view, but once you have this property, then everything that follows from there, you also observe. For instance, you observe the same scaling of this time scale, how long it takes to decode information. We have done it explicitly. My student, Misha Banchenko, and I, we took that system and we said, okay, suppose I have this system in laboratory and I store some information in that system and I want to decode this information by, let's say, scattering external light. How long does it take? And if you map scaling, it takes exactly what people thought about black holes, so-called Page's time. So you see, everything that is related with information and time scales, you sort of recover. Of course, you cannot recover everything. That would be too naive to expect it, right?
Okay, a last question.
Since you have mentioned string theory, what do you think about these solutions, fuzzy balls, that claim they solve the singularity because the singularity disappears and...
Well, okay, I mean, yeah. Sorry, I'll let you finish the question.
No, I was asking only your opinion.
Right, so, I mean, there are many other questions that you can ask about black holes, right? For example, one of the questions is singularity. What is the role of singularity in all this, right? Now, of course, everybody understands that singularity is normally simply... singularity, by the way, singularity is very good when you have it in a theory, because singularity indicates that that's where your description breaks down, and you have to change your theory to something more powerful. That's what happens for the electron is singular, but we are not worried about that. So, yeah, so singularity, black hole singularity is telling us that in around Planck length, once our distances that we want to probe become comparable to the Planck length, quantum theory of gravity, if I simply quantize Einstein and use, that theory becomes strongly coupled, okay? Strongly interacting. Now, with strongly interacting theories, you need some more powerful techniques or some other theory, some other way to compute things. So, now, I'm not addressing that question because our approach is very simple. We are dealing with large black holes, and our assumption is that the information properties of large black holes should not depend on the ultraviolet completion of your theory, because large black holes you can form by using only soft processes, and so it should be understandable in the language of these soft processes. Now, I'm sure that there are more than one ways to understand black hole physics. and they are probably all equivalent. So it could very well be that there is a different language. So, I mean, language is never the only one. So it could very well be that, for instance, in string theory language, you can understand the same answers you can give in a different framework. However, what I'm saying is that, and also our calculation shows that when you are in kinematic regime of very soft gravitons, the string theory gives you the same answer as quantum field theory computation. As it should be, because you see, look, we have in physics the notion which we call sometimes decoupling, or right? We have this notion that the theory, whatever theory we have at very short distances, cannot affect validity of a large distance theory. Now, we know that we don't need ultraviolet completion of gravity to compute Newtonian law or to compute Mercury perihelion, right? So Mercury perihelion, these kind of things, we can compute either in quantum language or classical language within Einstein gravity. And this has been done, and this is known. And this tells you that, of course, all the corrections to big objects from very short distance physics must be small. That's our assumption, okay? Now, maybe there are exceptions. That's a separate story. But even when there are exceptions, usually there is an equivalent language. But the new language is not destroying the old language of low energy theory. I mean, the language of low energy theory is surprisingly robust. And it's always valid. This is not excluding that there may be other language which is good enough, but is not based necessarily on effective field description. That's a separate story. But I'm not going there. So.
Okay, thank you very much. And let me remind that he is going to give a seminar today at 4:30 in the seminar room. So thanks again for the nice talk.